back to our objectives. We want to be able to write functions from formulas, from graphs, from verbal descriptions and data. We did the formulas part yesterday, and it was the formulas that most people would remember and be able to use. So yesterday was, let's write a formula that has to do with the area of a circle, and let's make sure there's an R in it. And then we changed that, did a little substitution so that we could use diameter instead. And then the third one, which, like I said, I think if you're going to make a useful formula out of this, that one might have been the best one, because circumference, if you wanted to work backwards to the radius, would take a couple of steps. So it would kind of be nice to know what the circumference is and just be able to punch it in there and figure out what your area is going to be. And then we did one of these fabulous maximum value problems. And maximum volume is one of those things where we probably did 2 or 3 of them as examples in Algebra 2. And then you maybe had 5 or 6 during the course of the year that you had to maximize the box. So this wasn't really new. It wasn't. But it's a good refresher, if nothing else. And that's what we needed. So now, what are we going to do? Well, we've got to move on to talking about graphs. I mean, what if you have a graph and you want to figure out a function that will represent what's going on with that graph? Well, the first thing you want to do is recognize it, hopefully as one of our 12 basic functions. And this one says we're going to protect an antenna. It's down in Maple Plain over, well, every weekend our church is down there. And these people had this huge, huge dish sitting outside of their house. You know, most people have a little one that's sitting on your roof. And these people, it was as big as I was sitting there. So they must really like their TV. They were hitting every satellite they possibly could. So this one is just a small satellite dish, and it's packaged with a cardboard cylinder for protection. So here's the dish itself, and then this brown piece that we see in here, that's the big, thick cardboard cylinder that they're putting in there to make sure that it doesn't get damaged as it gets shipped to you. So the parabolic dish is 24 inches in diameter, so there's the 24 right there, and it's 6 inches deep. The diameter of the cardboard cylinder is 12 inches. And with this one, I'm really glad they gave us a picture of it, because I'm not sure that everybody would recognize that when they say that that's the diameter, that that's what they mean. So this is really kind of a big, awkward-looking cylinder that they have in there with a 12-inch diameter. And they want to know how tall must the cylinder be to fit in the middle of the dish and be flush with the top of the dish. So sit in there nice and straight so that it's doing something to protect the bottom, but then it comes right up to the top so that it's actually giving some support from the top of that as well. So the first thing we do is think, okay, how on earth are we supposed to take something like that and make some math out of it? And what you want to do is you always use the Cartesian coordinate plane to your advantage. And start thinking, what would be the easiest way, because that's pretty obviously a parabola, to write an equation for a parabola. Well, if you have the vertex at 0, 0, that takes h and k out of play, and you don't have to worry about it. So the best thing to do would be to say, you know what, I'm going to make this 0, 0, and I'm going to put it right there on the Cartesian coordinate plane to make this work. And if we do that, that's going to split this 24 up into 12 on this side and 12 on this side, and it gets us a start. Because when I look at that, I think, well, if it's centered at 0, 0, and there's no h and k, all I need to do is find a. That's all I have to do. Because pretty obviously this is a compression. It's not going through 1, 1, 2, 4, 3, 9. It's been smushed down. So I need to figure out what a is. And to find a, all I would have to do is find an x and y on my parabola and work backwards. Now, there's one with negatives here, but if we don't want to work with negatives, why would we? There's a nice positive over here that has an x of 12 and a y of 6. I'd use that one instead, and that will get me a. So my y value was that 6 equals a. X value is 12. And we say, okay, 12 squared, that's 144. I know that one, that's 144. So 6 equals 144a. Well, we're going to divide, and we're going to see, can we reduce this? Which, yeah, we're going to use the calculators today. Who needs, while you guys are cranking that out and reducing it? Just one of them? 2 of them? otherwise you're going to need one today. Okay. So, or you could just reduce it in your head. Say, all right, 6 does go into 144. Let's see, 6 goes into 14 twice. Remainder of 2, 6 goes into 24 4 times. So, we get to that 124th one way or another. But what that just did was it allows us to get a formula for that parabola. It will be y equals 1/24 x squared. Now, that's not our answer, but that's huge. And if we have a formula for it and something's missing, then we could use this. So, what did they want us to do? They want us to place that cardboard cylinder in the middle of this. And again, best placing would be that cylinder is 12 inches across. It would be making sure that we have 6 units here and 6 units here. Splitting that right down the middle as well to give us some easy placing. But they wanted to know how tall must that cylinder be in the middle of the dish and be flush with the top of the dish. So, well, I already know what it's going to be here. The y value for the top is 6. So what I'm going to have to do is figure out, well, where's the bottom of this thing? Because it doesn't go all the way to 0, 0. And then I could just do some subtraction and I could figure out how tall it must be. Well, if I place this right, my x value is supposed to be 6 because it was 12 total and there'll be 6 on one side and 6 on the other. So if I put x equals 6 into my formula, that ought to tell me how far off the bottom of the parabola that little cylinder is going to have to sit. So let's see. We'll get y equals 1/24 of 6 squared, and that's 36/24, which 12 goes into both of those, and we get 3 halves, but it's a word problem. So we would write it as 1.5 inches. All right, so here's what I know. I know that this is 6 inches deep, and I now know that this y value is at 1.5. So how can I figure out how deep the cardboard piece is? How do you figure out the distance from 6 to 1.5? You just subtract. That's all you do. I was thinking back, and except for maybe exponential, you probably haven't done something like this. I mean, it's been a couple of years. In Algebra 2, what we typically did was we found 2 points that were on the parabola, used that to find A, and then wrote the equation, whether or not it was in vertex form or standard form. But this is a little different. You have to get that visual with it, So one of the things we always taught you in geometry was that, hey, if you don't know where to start, you draw a picture. That is exactly what you do. So if you're stuck, draw a picture. That's what we always do. And in this case, it goes a little further by reminding us, if you get to pick where you're going to put this on a Cartesian coordinate plane, pick something nice. Don't pick something that's going to require a lot of work. Put that vertex at 0, 0. Make it easy on yourself by placing that. So if they come with pictures, use the pictures. If they don't come with pictures, draw a picture. So this one says we're going to form functions from verbal descriptions. Well, here we go again. There's another little piece of our objective right there. So grain is leaking through a hole in a storage bin at a constant rate of 8 cubic inches per minute. Okay? The grain forms a cone-shaped pile on the ground. That kind of makes sense. So we got a little cone going here. This grain is falling down in there into that cone-shaped pile. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to its radius. Well, that's interesting. So this and this are the same. So they're both radius or they're both height, however you want to think of it. And then it says, if the cone is 1 foot tall now, how tall will it be in 1 hour? All right, let's look at the math we have so far. told us up here 8 cubic inches per minute. So there's the starting place. And then later on, it says if the cone is 1 foot tall now. Uh-oh, that's a problem. This is in cubic inches. Can't use 2 different labels. So we right away would say, you know what? Right now the radius is 12 inches. So we'll just use the 12. We'll convert everything to inches. They can keep the foot. We don't want that. We want this information. So what I would want to know is, what's the volume of this thing right now? I mean, we need a place to start, and that would be, hey, the grain is on the ground. What's the volume of the grain that we have right now? Then we can figure out how much grain is going to be added to it in the next hour, and then go from there. So let's just go that far first. So this is the one I said, it's a good thing we wrote that one down. Most people don't remember the volume of a cone is 1/3 pi r squared h. They just don't. So we've got a radius of 12. So our volume is going to be 1/3 times pi. But the radius equals the height. So if we put 12 squared times 12, that seems kind of silly. What could we put instead of 12 squared times 12? 12 to the third. Why not? Because remember, in this particular cone, the height and the radius stay exactly the same. Now, we are not going to punch the pi piece in. What I need you to do is punch in the 1/3 times 12 to the third and see what you get. We should get a nice number at this point. Because if we start putting pi in now, we will start rounding too early in the problem and we'll have rounding errors at that time. So what number goes in front of our pi? 576. So right now, there are 576 pi cubic inches of grain in that pile. We don't want right now. We want to know in an hour what's going to be there. And this is the growth rate that's occurring right now. Well, this is per minute. How many minutes are in an hour? 60. So we're going to go ahead and use a little unit analysis here. And unit analysis means we match up the labels on the top and the bottom so they cancel out. We know that there are 60 minutes in 1 hour. So the minutes are going to cancel here, and we're going to have cubic inches per hour, which is exactly what we want. Now, 8 times 60, that's 480 cubic inches per hour. So that's what's going to be added to this in an hour. So this was, right now, here's the pile. In 1 hour, it will have a volume of 576 pi plus 480 cubic inches. Okay, that was a good start. We saw this is the volume right now. We're going to add 480 cubic inches to it in an hour. Now, what did they want? There was a lot of blah, blah, blah up here. If the cone is 1 foot tall now, how tall will it be in an hour? Oh, so we have the volume in an hour, and we want to know how tall it's going to be in an hour. Well, it would seem we better probably use that volume formula we have up here. Well, wait a minute. Something cool happened with this one, right? What do we know about the radius and the height? They're the same. So remember yesterday, we had to use whatever variable it was that they wanted us to use for this. Well, this is asking us how tall it's going to be in an hour. So should we be using the r or should we use the h? Yeah, h, we want to know the height. So we'll do h cubed this time instead of r cubed, because what we care about is the height. Well, we know the volume, so let's put that up here. As ugly as it is, let's put it up there. 576 pi plus 480 equals 1/3 pi h cubed. We want to get h all by itself. So give me a step. What would you do? Yep, get rid of that fraction. Multiply both sides by 3. Now, I'm not actually going to do the multiplication right now. I'm going to hang on and punch it in all at one time. And that's because I want my answer to have no rounding errors, no matter what. Now, we can distribute this 3 and it won't make a difference, but I think it's easier for me to show you what we're going to have to practice later on this semester, which is just letting the calculator keep those perfect answers in there for us. So we've got our 3 times 576 pi plus 480. And that equals pi h cubed. Give me another step to get h by itself. Divide by pi. All right, so looks like that. Almost there. To get h by itself, we would cube root all right, that will get us h. So like I said, what we're going to do is we're going to let the calculator store all this stuff so there's no rounding errors at any point. So what we'll do is we're going to use what's called the answer key, and that pulls up the last thing you punched in. So we will punch in with parentheses so the calculator knows all of this stuff on the top multiplied together, divided by pi, and then we'll let the calculator divide, or actually take the cube root. So let me show you how we'll do that. All right, we're good to go. So we had a 3, parentheses, 3, and we wanted that times, parentheses, 576 pi, and pi is second caret symbol, plus 480, parentheses, parentheses, so that'll take care of multiplying by the 3. We're going to divide that by pi, so divide, second caret symbol. And now you think, hey, it's just holding on to those decimals. It's not. That little chip that's inside of this is holding on to the entire answer in there. So this is still perfect. We don't want to write anything down at this point. We want to keep going with the math. So what we want to do is cube root. Cart. Oh, thank you. Let me pull that back up. Oh, let me go ahead and punch it in again. 3, 576 pi plus 480. Didn't take the 0 again. There we go. Divided by pi. Now we need cube root. So math and number 4. And now we're going to tell the calculator, just take the last stuff that we punched in and take the cube root of it. And that has these little blue letters down here, A and S, and that's on the negative button. So we'll hit second and negative button. And then it is. So again, the calculator is keeping all of those decimals for us so that we don't round. Every time we stop and round and we use that math for something else, we produce a rounding error. So let the calculator do the whole thing. And we would go with 12.979 inches for our height here. And that's what they wanted to know. They wanted to know how tall this is going to be. So we're using formulas. Sketch didn't hurt. You know, it makes you think about the fact that you've got a cone here and what's it going to look like after an hour, how much would be in there, and then you can work your way back to the height. So we could strike that off the objective there. That one was our functions from verbal descriptions. Basically a word problem, you know, all the way from the beginning. Now, in this problem, we had to use a step that was called unit analysis. In science, it's called dimensional analysis. And we had to do that twice. First, when they told us this information in cubic inches, and then they told us that this was a foot for the radius. You can't do that. You need the same units all the way through. So we had to figure out, hey, there's 12 inches in a foot. And then they had 8 cubic inches per minute, and we wanted to know after an hour, how much is that going to be? So we made sure that our labels canceled on the top and the bottom. Now, the reason I'm bringing that up is because we're going to do a This next problem has a lot of unit analysis. So we're going to let the units work for us, the labels. Let the labels guide us. It says, how many rotations does a 15-inch radius tire make per second on a sport utility vehicle that's traveling 70 miles per hour? So, two pieces of information here. We've got rotations with a 15-inch radius tire. And then we have 70 miles per hour. Well, that's where I'm going to start. We'll wait and see how the rest of the information fits in with what we have. Because what they want for an answer is rotations per second. Rotations per second. Now, I don't see rotations up here at all with this piece, but I certainly know I could work this hours into something about seconds. So what's something helpful that you know about hours that might help us get to seconds? 60 minutes in an hour. So the way we're using dimensional analysis here is saying this had hours on the bottom. We don't want hours anymore, so we're going to put hours on the top of the next fraction and get rid of that. So now we're in minutes. Is there something helpful about minutes that you know that might help us to seconds? 60 seconds in a minute. I want those minutes gone, so I'm going to put a minute up here and 60 seconds down here. So right now, we have miles per second. That's not what they wanted. They wanted rotations per second. Okay, well, we've got the second part. Obviously, there's something about rotations that we're supposed to know here. Let's see. A circle. When you make a rotation, oh, one rotation of a circle, what's that called? Circumference. So we probably better look at what the circumference is going to be. What's the formula for circumference of a circle? 2 pi r. So this circumference is going to be 2 times pi times 15, which will be 30 pi. Now the labels are important. We know that about this problem. 30 pi inches in one rotation. So I have this 30 pi inches in one rotation. I don't like my 30, my 0 didn't show up very well. Weighting in the wings. Obviously, I'm going to have to use that because it has that rotation piece that I need. But the other part of it is down on the bottom, it has inches. And right now, I'm stalled out at miles. So I'm going to have to think, how can I get miles to be something about inches? So do you remember anything that might be helpful with miles that might lead us to inches, Shelby? Excellent. And I know I'm going to run out of space here for my unit analysis. Right now we have 70 miles, and we know 1 mile is 5,280 feet. I'll just put 1 miles, and it's grammatically incorrect. Miles are going to cancel. So now we're at feet per second. We need to work our way to inches. So what do you know about feet and inches? 12 inches in a foot. All right, so I'm going to need something about feet in the bottom, so it'll cancel out. 12 inches in a foot. And yeah, I have to go down to this next line because I am totally out of space. Too big. Now, looking at everything we have, we would have inches per second. And now I can figure out what I need to do with this last one. Because I'm not supposed to have inches as my label. I'm supposed to have rotations per second. So what am I going to have to do with that 30 pi inches per 1 second? How will that help cancel this out? Flip it. Yeah, reciprocal. 1 rotation, 30 pi inches. And look at how the inches are going to cancel. So of all the labels on the top, all we have left is rotation. And of all the labels on the bottom, all we have left is seconds, and that's going to give us rotations per second. Now make sure you use parentheses when you're multiplying all this. Numerators times numerators divided by denominators times denominators. So parentheses 70 times 5,280 times 12 parentheses divided by 60 times 60 times 30 times, don't forget the pi. People always forget that. That's when they get this one wrong. So go ahead and punch that in and let's see if everybody can get the same amount of rotations per second. Parentheses for everything in the numerator divided by parentheses for everything in the denominator. Everybody getting the 13.072? Good. Yeah. If anybody forgets anything, it's usually the pi. You know, we're looking for numbers as we try to do that multiplication, numerator times numerator, denominator times denominator. And we miss that little pi down there. Otherwise, it's pretty basic use of fractions, you know. But that's human analysis. You know, you're always just working, okay, what is my next label? What does this have to be in order to get me where I need to go? And thinking about those next steps. So that's a pretty big one. I would guess in physics you probably had to do at least 7 conversions before to do some problems. Yeah. I mean, I remember some physics problems where basically it was half a page of converting to get to where you need to go. So that's another good part to our objective. And then this last one is we're going to give you some data. There's a lot of blah, blah, blah here, but most of this is stuff that we've talked about before. So forming functions from data. Starting at the very beginning, here's all the numbers we collected. Give us a formula that'll work for this. It says, given a set of data points of the form ordered pairs x, y, to construct a formula that approximates y as a function of x. Make a scatter plot of the data points. The points do not need to pass the vertical line test. We're not saying functions here. We're saying let's represent this data, get some kind of model that we can use to make predictions. And number 2 says, determine from the shape of the plot whether the points seem to follow the graph of a familiar type of function. Our 12 basic functions. You know, maybe you look at the data and you say, ooh, this isn't really linear. It's not looking like this is going to line up. But when you take a second look, you notice they're kind of curved, like a parabola. So you could do quadratic regression. Or maybe you notice, hey, this seems to be forming that sine-cosine wave. And maybe I could do some trigonometric regression on this thing. We're not going to do that, by the way, because we're not real solid in trig just yet. But look for those things and figure out which regression you should do. And then transform one of those basic functions of that type to fit the points as closely as possible. And these words right here are telling us we should use a graphic. You know, as closely as possible. We could draw a pretty good line of best fit, and we could get a halfway decent equation for that. But the calculator uses a process called least squares regression that we just can't do by hand without a lot of extra time. So we're going to turn it over to the graphing calculator. Curve fitting with technology. Table 1.12 down here records the low and high daily temperatures observed on, they picked an interesting date there, 9/9/1999 in 20 major American cities. We want to find a function that approximates the high temperature y as a function of the low temperature x. Use this function to predict the high temperature that day for Madison, Wisconsin, given that the low was 46. Okay, so how do we start? We got to get all this stuff in the calculator. They said use these as your x's and these as your y's. And we've got to get them into our lists. So we're going to put this into list 1 and list 2. And we will just put all the lows in as list 1 and all the highs in as list 2. And then we'll start seeing whether or not we should use linear regression, should we use something else. And because this thing has been klutzy and slow, So if we go to stats, number 1, edit, that's where you need to get your lists in there. And I can see a whole lot of you already putting in. So go ahead and put those lows and highs in, and then we'll get back together here and see what we need to do. Keep going. Just lay down my action. Is going to be, we need to see it. We need to see whether or not it looks like a line would run through this data or a curve, what's going on with it. And that's always the stat plots. So second, y equals, this is where we do all the graphing with statistics. Go into number 1, and when Blinky's on the top of the on, hit enter. That'll turn it on. And then we have to make sure that the lists that we use for the data are the same ones we see here for X list and Y list, or list 1, list 2. If it's not, hit second, number 1, that'll give you list 1. Second, number 2 will give you list 2, etc. And we're not going to see this if we do negative 10 to 10 window, because that's not the numbers we put into this. So when I looked at the data, I thought, you know what, none of the lows got as low as 40. In fact, I think the lowest number they had there was 52, so I should be safe with using a 40. And then none of them really got higher than, what was it, the 80s? Yeah, Phoenix was at 82, so I just went with 110, making sure I can see all of that. And then the Y values, these were higher temperatures, so I just scooted that up to 60 and 120 for the high temperatures. And yeah, it's probably a little bit more than we need, but we'll be able to see all of the data. So now if we hit graph. And yes, we got caught with the fire drill last hour. That was right where we were at. It looks like this. And you know what? It wouldn't be a horrible line of best fit. You try to keep the same number of points above and below. It wouldn't be horrible to make a linear model for that. But I guess the question would be, how bad is not horrible? So I would want to know, if I do the regression, is it a good line of best fit? And in order for that to happen, we have to make sure that our calculators are going to give us that little correlation coefficient, the R. And some of you may have had to clear memories and stuff like that since the last time we did this. So let's go ahead and make sure that those R values, the correlation coefficients, are turned on. And that's going to be in the catalog again. So second, 0 is where we see that catalog. And then we need to go down to diagnostics on, and we need to hit enter twice. And I tried to do the shortcut this morning, and it wouldn't let me. Yeah, it still won't. So I'm going to go down to, it might take me a little longer than you. Diagnostics on, and hit enter twice. The first enter just tells the calculator, yes, this is what I want you to do. The second one says execute it. So that makes sure we're going to see an R value when we do our linear regression. So now, this is where we have issues because everybody has different calculators all over the room. But we all go to the same place, stats, calculate, And number 4, linear regression. But some of you don't see this screen. So what you're going to have to do, yours says something like Lynn REG right now, is pull up list 1, comma, list 2, comma, and then wait for the rest of us, because what we're going to do is we're going to make this store it in that Y variable for us. So I want list 1 and list 2. Yes, I don't care about the frequency of the list, but I don't want to have to do all the math by hand with this if I can get the calculator to store it. So now everybody's at the spot where those that have the older calculators, you're waiting for a Y variable, and our calculator is waiting for a Y variable. So we have to go get it. Do you remember where those Y variables are? Been too long? Yeah, we don't use it a lot. VARS. It's just to the left of the clear key, and we want Y variables, so we're going to hit the right arrow, and we do want functions, so we're going to hit number 1, and then we can just pick Y sub 1. Everybody will have everything stored in Y sub 1. And now those of you that have the calculators where you had to use the commas, you should be able to just hit enter, and the rest of us are going to hit enter on calculate, and it's going to do the linear regression for us. And it's also going to give us an idea of whether or not that was a good thing to do or not. Our R value to 3 decimal places would be 0.899. So we have to ask ourselves, is that a pretty decent R value or not? Well, remember, 1 is perfect. So that's not too bad. I mean, it's not perfect, but it's not too bad at 0.899. So the calculator says, you wanted this, we gave it to you. Here's the A you should use, and here's the B you should use if you're going to write that formula. So it would be Y equals 0.970, with rounding to 3 decimal places, X, plus 23.015. And I'm going to go back and write that down so that we can do the rest of this math. Now that we have our formula, we can make predictions about what they wanted. And what they wanted was to know, predict the high temperature for Madison, Wisconsin, if it's low, was 46. Well, if I don't have to plug the 46 in, I don't want to plug the 46 in. And it turns out I don't have to because I stored this in my graphic calculator. What I can do instead is use the table feature. But of course, that's at 0. I'd like to see 46. Do you remember how we can get the table to jump to 46 for us so we don't have to sit and scroll all day? Table set. So second window, and I'm just going to tell it, hey, I want to know about 46. And then second table. There's the first one up there. Now, we know we're supposed to go 3 decimal places. So yes, we would still put the 46 into the formula and actually see what it is. But at least this would give us an idea of whether or not we've done the math right when we get done. So we go back to our formula. We needed 0.970. Might not use a 0 in that spot again. There we go. And we wanted to know about that low temperature of 46. And then it was plus 23.015. So 67.635 degrees. That was pretty close to what we saw in the table. So at least we know we did the math right as we went through there. So with their low of 46, Madison, Wisconsin should expect a high of 67.635 degrees. And like it says, the little note down here, keep this data and equation on your calculator. Probably going to need this again. And there might be one in the homework where they actually ask you about this. So that might be one of the reasons that we're going to do that. But I know we're talking about it on these next 2 pages that are filled with blah, blah, blah here. So this one says professional statisticians would be quick to point out that this function should not be trusted as a model for all cities, despite the fairly successful prediction for Madison. For example, the prediction for San Francisco with a low of 54 and a high of 64 is off by more than 11 degrees. You know, it's just 1 year's data. It's not multiple years. So the effectiveness of a database model is highly dependent on the number of data points and the way they were selected. So they really didn't have enough. I'm sure it felt like enough points when we were having to type them all in, but you really need a large number of data to support any kind of conjectures you're going to make about something. The functions we construct from data in this book should be analyzed for how well they model the data, not for how well they model the larger population from which the data came. And just a little reminder here that we have different, we've got talked about the 12 basic functions. Now we have all different kinds of regression that our calculator can do. We can do linear regression on a graphic calculator. We can do quadratic. We can do cubic. We can do quartic. We can do regression, and we haven't yet, but we can do it with the natural logarithm. We can do that. Our calculator does it. We can do exponential regression, and whether or not we have growth or decay, those are 2 things we can do on our calculator. And then we have a power function that we can do regression on. We can actually even do logistic regression. You know, the one for populations. Our calculator is capable of that. Sinusoidal, we actually don't do that this year. We don't do any regression that involves the sine or the cosine function, but it's possible. You know, it's all there. It's in our calculator. We just have to access it. So these graphs are only examples as they vary in shape and orientation. For example, any of the curves could appear upside down. The grapher uses various strategies to fit these curves to the data, most of them based on combining function composition along with linear regression. Depending on the regression type, the grapher may display a number R, which is the correlation coefficient, and that's the one we were looking for. And in some regressions, it only gives you R squared, which in some books is called the coefficient of determination. But in either case, your rule of thumb is the closer it is to 1, or the absolute value of 1, the better it is. So it says, look back at our temperature data and the linear regression equation that we found, and our correlation coefficient was approximately 0.899. Now there's actually 2 things that tells us. What it tells us is it's a pretty good line of best fit, but it also tells us the slope is positive because this was a positive number. So positive slope and a fairly good line of best fit. Not too bad. So in that little box down here, it says if you don't have an R value, remember you can go to the catalog, you can turn on your diagnostics, and then you can see your R squared or your R value from there. Alrighty, so that was 1.7, and we had the rest of our formulas, graphs, verbal descriptions, and data. Bless you. Alright, so what you want to do is finish 1.7, and then, so that we don't feel rushed tomorrow during the review day. The review this time is coming from a packet, so we're only going to do the circle problems. We've got some spares in here in case anybody wants to do extra, but you don't have to. I probably would just do the circled ones on the front and back of this. So finish 1.7 and then put a short check. Yes. So don't work through this whole thing because we will be working on this tomorrow. Finished 1.7, like I said, I guess the front page, front and back of the yellow, I would try to get through. Yep, thank you. call it Lisa Fire Building Block.
I'm gonna make on maps and then anything else.
I dribbled down on that hat.
Okay.
You said.